Hello and welcome to another chemistry topic together. As you can see, our topic is the 5 types of reactions, and you can start setting up your focus notes. Start by filling in the topic and the date. The date this was originally assigned was January 20th, 2021, but fill in whatever date you are taking these notes because you might be watching it during a different term than when I made this original video. So then after you set up your topic and date, our essential questions we're going to answer in this lecture are: what is the difference between combustion, synthesis, decomposition, single replacement, and double replacement reactions? So the idea here is that we can sort of classify reactions in certain ways, which will help us understand the chemistry that's going on. Like if we know something is synthesis, that helps us predict what's going to happen on the product side, or combustion or double replacement. It will help us as a chemist kind of tell the story of what's going on. The other EQ is what factors affect the rate of reaction. So let's say we've identified something as single replacement, which at some point you'll know what that means after this lecture. So we know it's single replacement. What will make that reaction go faster or slower? So that's what rate of reaction means, how the speed at which the reaction takes place. Because maybe it's a reaction that's dangerous, so I'm trying to slow it down so it doesn't produce as much. Or maybe it's a reaction that's really expensive, so I want it to go slower. Or if the whole point of my reaction is to make something, then of course I'd want to speed it up. This could be important for spreading of a disease or cancer cell reproductions. Could I do something to slow it down? Those kinds of things are super useful. So rate of reaction is something that chemists start to think about. So the cool thing about today's lecture is that it starts to obviously build on just your foundation knowledge of chemistry, but it starts to now put applications of things. So it's not just about writing a reaction that's already been given you, but predicting products and starting to think about, I can predict what's going to happen in this reaction, and starts to get into some more interesting things and deeper level of chemistry. All right, you got your notes set up, ready to go? Let's get started. So just a quick review of some things that we already know. We know that it's going to be considered a chemical reaction when old bonds are broken and new bonds are formed. But remember, the tricky thing is that you can't watch an atom break a bond with another atom and reform with different atoms to make something new. So remember, we're looking for one or more of the 5 signs of a reaction to confirm that there has been a chemical change. And you can jot these down if you need to again, but remember the signs we're looking for are one or more of these things. So temperature change, light given off; precipitate, color change, usually with something else; and then gas given off. So if we see those things, then that's our clue. Oh, this is a chemical change. Old bonds have been broken. New bonds have been formed. What would that reaction look like? And then we move forward. So there are 5 types of chemical reactions, and the more you study chemistry, the more you might learn about some details related to these and some other special kinds of reactions. We're going to focus on these 5 for this course. The more chemistry you learn, the more you'll learn about different ways we categorize things. So synthesis, decomposition, single and double replacement, and combustion. All right, let's get into it. Let's start with combustion. Now, even if I didn't have this picture up here, probably you have a picture in your mind of combustion is like fire, it's burning, right? Well, here's the chemistry behind it. You need to have a carbon-based molecule that's your fuel. So if you think about any time you've seen fire, there's something burning. So whether it is some type of like gasoline or propane or something like that, or whether it is logs on a fire or something, or forest fire or something, those are your carbon-based molecules. There has to be oxygen present for something to burn, and then it always produces CO2 and H2O. So it's a really specific chemical reaction. It can only be combustion if it has these 4 pieces: some type of fuel, which is going to be your carbon-based molecule, and then oxygen producing CO2 and H2O. So your clue to recognize a combustion reaction, so again, eventually this is a toolkit you'll use as a chemist to predict what's going to happen. So if you see a carbon-based molecule and oxygen, you know there's going to be combustion. So you've got 2 ways you can think of it as a clue. If your products were given and the products are CO2 and H2O, you know it's combustion. Or if you start with a carbon-based molecule, you can be pretty sure that that's going to be a combustion type reaction. To go with combustion, just to kind of make some connections in your world, I have a special reading for you in this unit about combustion. It focuses on complete versus incomplete, and actually something that might affect something in your home. So what I want you to do is, if you have access to a printer, actually print this reading, and you're going to tape it into your notebook on an output page as a flip page. So tape it on the side, and then you can like fold that in. or just put it into Notability with your other handouts. You read it, and then there's some processing on the back to kind of make sure it makes sense. So just kind of a special connection to something that maybe you've heard of, but something to just connect to your life with a little special reading. Okay, and then go ahead and do a level 1 question so far. So about any of our notes, just something right from the notes, just kind of a basic question, just a sort of process. Are these things making sense so far? All right, and then because we're talking about reactions, come on, we've got to do some demos. So we're going to do our combustion demo at this time. All right, well, welcome again to demo time. So the demo that I'm going to do here is for combustion. And because of the definition of combustion, or what you know about that word, you maybe already kind of have an idea of what's going to happen, but I don't think we ever get tired of watching it, right? Okay, so what I have here is methanol. The formula for methanol is CH3OH, so that's my carbon-based molecule. Plenty of oxygen here in the room, so that will be my oxygen. So remember, the definition of that makes it methanol is that the definition that makes it combustion is that you have a carbon-based molecule plus oxygen. And then this is one of those times when we can actually predict the products. We know that after I do this reaction, the leftover things in the bottle will be carbon dioxide and water. So that's what we're looking for. So let me just kind of move this out of the way for now. All right, so right now there's already a bunch of carbon dioxide and air and water vapor and all the stuff that's in air in this bottle, but I don't want that to be in there. So what I'm gonna do is I'm gonna cover anything that is inside that bottle with methanol fumes, and then I'll open the bottle back up so there will be some oxygen that can replenish and make this reaction happen. So all I'm doing right now is just making sure that the only thing that matters in there is the methanol fumes. And then I'm going to pour out the liquid methanol, because that's actually not the part I care about. And then I've got that bottle ready to go. I need a little spark. All right. So hopefully you saw that blue flame, kind of like an engine rocket or rocket engine. So this idea of, okay, so there was that combustion reaction that happened. It used up that energy, light energy, heat energy, you can tell, because the bottle is getting kind of melted. And then you can see there's a little bit of condensed water vapor. So the water vapor got really hot, but then also cooled back down. So I got some water vapor in there, and then there would be some carbon dioxide floating around in there too. So definitely a chemical change. We saw the light, we can experience the warmth. The bottle is melting, the bottle's a little bit warm. And so for sure a chemical change, specifically combustion, because I started with a carbon-based molecule, there was oxygen present, and I produced CO2 and H2O every time. Combustion. All right, so the next one we're going to talk about is the synthesis reaction. Now, it's possible you've heard of this word. If you're synthesizing ideas, you're putting things together. So a synthesis reaction, by definition, is you have two or more reactants that form one product. That is the key. So your clue, if you are looking for a bunch of different reactions and you're trying to figure out what the synthesis is, if there's only one product, it's going to be synthesis. It has to be. So if things combine, everything bonds and comes together, that's a synthesis reaction. And once again, we're talking about reactions, we got to do a demo. So here is your second demo for types of reactions on synthesis. All right, for our demo time for synthesis, I actually am going to play a video for you. I'm sorry if that seems like I'm cheating a little bit, but it turns out that actually synthesis reactions are really hard to show, and this is a really good video. They can do it just as well as I can, so I might as well take advantage of the resources that I have. So check out this. So we're going to watch the reaction of iron with sulfur, and it's initiated by heating something. So if you think about how you would draw the reaction, you'd put the word heat or that little triangle over the arrow, and it's going to produce iron sulfide. And notice that it doesn't give you the Roman numeral for iron sulfide, so you would have to actually do both of them and then figure out which one that you had. All right, let's check it out. Let's see what we got for our reaction of iron with sulfur, initiated by heat, and then forming iron sulfide. Check it out. So you can see sulfur is kind of a yellowy powder. Iron is gray powder. Mix them together. All right, now this reaction isn't going to synthesize, or the two elements aren't going to come together on their own. So we need to add some heat. So they're going to use a glass stir rod and put it in the flame until that glass gets red hot. Now you can see the red kind of glowing, but that's just the tip of the rod. So you need to keep it in there for a while. So we're going to take advantage of time lapse, because this takes a little while to get the really, really hot, and then you put the really, really hot stir rod in there, and look at that, fireworks! So it's releasing energy as the atoms come together and become more stable. Looks kind of like lava, so light given off, temperature change, color change. So letting that reaction finish just a few moments. And then there we go. You can see it forms kind of this hardened compound, the iron sulfide. So that idea of elements coming together is synthesis. So it forms one solid product that is now iron sulfide. All right, thanks so much. There's your demo time for synthesis. All right, the next one we want to talk about is decomposition. And again, this is a word that we use in different contexts, so it's possible you can sort of predict what's going to happen. If something is decomposing on the side of the road, in a compost bin, on the side of, in a forest somewhere, whatever, it's breaking down. It's breaking down into its pieces. So the definition of decomposition is that you have one reactant that is producing two or more than that products. So this, a little side note for you, this is actually how airbags work. So airbags have sodium nitride in them. It's a solid, kind of like a little powder. And what happens is when there's some type of spark in a crash or an accident, that causes this reaction to go. So otherwise, this is pretty stable. And then when there's some type of spark or heat or electric shock to that airbag, what happens is it splits into a different version of sodium nitride and then nitrogen gas. And nitrogen is a safe, non-flammable gas, so that fills up the airbag. But then if it were to get punctured and you breathed it in, it wouldn't be a problem. It wouldn't explode. So obviously the chemists were smart when they chose this as what's inside airbags. But that's an example of decomposition. So your clue for decomposition is only one reactant. There's nothing else for it to do except split apart. So decomposition. All right, go into your level 2 question so far. Kind of think about compare contrast might be a great one. Sketch would be a cool one for this one. So sketch an example of what a decomposition reaction might look like. That might be kind of cool. All right. Okay. Of course, we have to continue with our demo. So this one is on decomposition, demo time. All right, welcome to demo time. The demo I'm going to show you for this one happens to be decomposition. So remember, the whole idea behind decomposition is that you start with one chemical. That chemical can't do anything else but break apart. So that's what we're looking for. So I'm going to start with a bleach. The main ingredient in bleach is sodium hypochlorite. So that is the chemical that we're really starting with. So if you're thinking about writing an equation, it'd be sodium hypochlorite. And then we're going to see what happens. Now, a lot of times this is, well, I'll say it happens quite a bit in chemistry, that decomposition reactions happen pretty slow. So right now, this is starting to break apart, but we're not really seeing any signs of a reaction. So it's hard to know that this is a chemical change, and I'm telling you it's supposed to be, so we got to do something. So I'm going to use a catalyst. The purpose of a catalyst is that it's not really reacting with the sodium hypochlorite, it's doing something to give like a new pathway for the reaction, so the reaction goes faster, and that's what makes it a catalyst. So I'm going to get a scoop of this. You can see it's kind of this like purplish reddish crystals, and when I add that, that's going to give the reaction a new path, and then that's going to allow the reaction to go a lot faster. So I put that in there. Okay, so for sure right away we see a color change, and then do you see what else is happening here? There's some fizzing, and then now you can start seeing some bubbles. So if we think of the reaction for the formula for sodium hypochlorite, there's oxygen in it. So we can be pretty sure that oxygen is being formed in there because of the bubbles, and then the leftover would be sodium chloride, solution still mixed in there. So when something is decomposing, basically it decomposes until it's stable. So oxygen is a stable molecule, O2. Sodium chloride would be a stable compound. There'd be no reason for the sodium to break off from the chlorine to keep decomposing because sodium and chlorine aren't stable on their own. So that's kind of the idea when you're predicting products for decomposition. Remember those tricks about what, sorry, it's kind of smelly. So I also know that gas is given off because of the bubbles and then also the scent. All right, so we know that gas has been given off because of the bubbles and the scent. We know there's a chemical change. I'm telling you it's decomposition. And when you're predicting products for decomposition, you're thinking about how much can it break down so that it makes a stable compound, no reason to keep breaking down. All right, decomposition. All right, the next one we want to talk about is called single replacement. And kind of like the term implies, something is being replaced, but apparently only one thing, so single replacement. So the definition of single replacement is you start with a single element and some compound. And then when the reaction happens, you now have a new single element and a new compound. So if we want to be a little bit silly, that's kind of what this picture is showing. So imagine you have a single person and a couple, right? And then at some point there's a new single person, that's maybe sad, and a new couple, right? That would be sort of the analogy if you wanted to think about people. So the tricky thing about a single replacement reaction is, and again, if you want to keep making the connection, this would be true with people also. A single replacement reaction can only happen if the single element is so attractive, it can split up the compound. So we can figure that out because we have a guide called the activity series, and that's a handout on Schoology. So you can download that into your Notability or print it, and it has a list of which elements are more active or reactive than others. The ones on the top of the list can replace everything below it. And so if those top of the list elements are the single element, they are attractive enough that they can pull apart that compound to create the reaction. The elements lower on the list are not so strong in terms of reactivity and attraction and that. And so if they are the single element, they won't split up that compound, and then you don't have a reaction that occurs. So when we're doing this, this is a skill that scientists learn for actually predicting products. So that's kind of your next level chemistry. Instead of me just giving you the reactants and the products and you write reactions, now you can start to predict what's going to happen using the activity series. So again, it lists the elements in order of reactivity, and you ask yourself, is the single element in this reaction more active than the thing it's trying to replace? If yes, then you switch their places, you balance the formulas, and you balance the equation. If no, you just put NR, no reaction happened. So let's try this. So Pb plus iron 3 nitrate. Okay, Pb is lead. So what you would do is you would look at, let's go through the steps. So Pb is the element by itself. It is a metal, so the thing it's going to try to replace is another metal. So Pb has a positive charge, it replaces something positive, so it can try to bond with NO3. So that's what's trying to happen. So you look at your activity series and find Pb and find Fe. Well, you'll find that Fe is higher, meaning that Fe is so attracted to NO3, Pb can't get in there and attract away the NO3. So this attraction, these ions are so strongly attracted that Pb can't do anything. So we're going to say Nr. If you mix these two in a beaker, you would see no signs of a reaction. The Pb, the lead, would just sit in the solution and nothing would happen because Pb is not attractive enough to split up this compound. So that's what I just said. So Fe is the more active one, and so the compound can't split apart. This attraction is too strong. The next one I want to try is sodium and water. But here's the tricky thing. When water splits up, it splits into hydrogen and hydroxide, not hydrogen and oxygen. So we write it as HOH because it's really an H positive and an OH minus that are creating that water molecule. So it's an H plus and an OH. So it shows you that that's how it splits up. Again, if you didn't write it like this, you would think it was H splitting up from oxygen and you'd get a totally different reaction. So let's write it like this. So sodium, you can see I already balanced this also. So we have Na, HOH, and then H2 and NaOH. Okay, so how did we know this was going to happen? Na has a positive charge and so does hydrogen. So you look on your activity series and you see that sodium is higher than hydrogen. So when these two things mix together, the sodium replaces H. So then H gets bumped out by itself, but remember you can't ever have just an H, so it's got to be diatomic H2. And then the sodium bonds with OH minus. Perfect match, Na plus 1, OH minus 1. So you get NaOH. And then I went through and balanced the whole equation. So 2 NAs, 2 NAs, 2 H's by themselves, 2 H's by themselves, 2 OH's, 2 OH's. So this was a single replacement reaction, again, because sodium is more active than the hydrogen. So hydrogen gets booted out of the compound because sodium and hydroxide are more attracted to each other. That's the idea behind a single replacement reaction. So again, since sodium is more active than hydrogen, sodium replaces hydrogen, makes a new compound, leaving a new element by itself, in this case, hydrogen. All right. So just a couple reminders when you're thinking about predicting products. Remember those diatomics, Brother Honcliffe. So remember, that's why we knew that hydrogen had to be H2. And then there are a couple exceptions that aren't technically diatomic, because that means two. Phosphorus is one and sulfur is one. So if you're doing a reaction where phosphorus is produced, just remember it's P4, and if you're, or a reactant, and then if sulfur is a reactant or a product, just know that it's S8. So it just has to do with the stability of their nucleus, and that just happens to be what they form instead of just a P or just an S. A couple other hints when you're predicting products, which will be especially useful if you're doing a lab situation and you see something happen and you're trying to predict what you saw. So in this order, go ahead and make a big point about that. You try to pull out CO2 from your reactants. If you saw bubbles and there's carbon and there's oxygen present, then probably you produce CO2. If you can't pull out CO2, maybe you produce HOH. If you can't produce water, maybe just oxygen or just hydrogen. So in this order, can you pull these things out from the reactants to try to predict your products? So that's kind of helpful for decomposition reactions when you're predicting products, and single replacement reactions also. All right. Okay. All of that said about single replacement, it's finally time to do demo. Let's check out this demo for single replacement. All right. Welcome to demo time. Single replacement reaction is what I have for you right now. So let's remind ourselves, in a single replacement reaction, you start with a single element. In this case, we're going to use aluminum, and then you need a compound. We're going to use copper 2 chloride. Now this copper 2 chloride, I've got two versions of it. They are both copper 2 chloride, even though they look very different. This one is called a saturated solution, meaning that I have as much copper 2 chloride as possible dissolved in the water in this liter solution. This has 0.1 molarity is what it's called. We're going to learn more about molarity later, but that's a common way that solutions are measured, telling me that I have 0.1, what is called moles per liter of solution. So very different what are called concentrations between them. And we're going to see if that seems to matter. All right. And then we'll talk about that next. So, but again, my reaction is between a single element, aluminum, and copper 2 chloride. So let's kind of think about what should be happening. Aluminum is a metal, and so it has to replace something that is also a metal. So between copper and chlorine, what's the metal? Yep, copper. So then we would look on that activity series and we would see the lineup and we'd be like, yeah, aluminum is higher than copper, meaning that aluminum is more attracted to the chlorine in these chemicals than the copper is. So the copper should be getting bumped out, and then we should be able to see that copper separated from the chlorine, and then the aluminum and chlorine will make a reaction or a compound instead. And then you could balance it from there. So let's go ahead and check this out. So I've got I'll try to use about the same amounts of both chemicals. And again, the only reason this looks kind of greenish is because there's so much chemical in it that it doesn't even look blue anymore. But it is both copper 2 chloride. I'm not trying to trick you, I promise. So we've got our two things here. We can see that the solutions look different. I try to kind of explain a little bit why they're different. And then similar size of aluminum, a little bit different. And then I'm going to kind of just rip them in little pieces just to give them a chance to react. And then I'll do that with this one too. All right, here we go. Let's check it out. Let's see if we can see anything happening. All right, what do you notice? Okay, this one is definitely happening, right? So there must be some reason why that one's so obvious. And then this one, yeah, there's something happening there. Like if you look at it closely, oh yeah, sure, there's something reacting. Maybe you can kind of see that copper color that's showing up on the aluminum foil here. You can see that the color is changing a little bit. If you look really closely, you can see a little bit of some bubbles. So there's definitely something happened there. There you can see the aluminum foil is changing color, kind of that copper color. This one, this is very warm, so we see there was some fizzing and steam that happened, so gas giving off, color change for that one, and that's probably it. I'm going to keep showing you this. Yep, there's definitely something happened there. So we're going to say that, yeah, this reaction is occurring. There's a color change. There's some bubbles happening in there, just not as obvious as this one. And so that's actually what we're going to talk about next. But back to just the idea of this being single replacement, definitely in both cases, the aluminum foil, which we're thinking of just as pure aluminum, replaces the copper in both of the solutions. So now the copper is floating around, which is why we get kind of that reddish, rusty brown looking color. And then there's aluminum chloride just kind of floating around in the solution now. All right, single replacement. All right, so you notice that there was two versions of this reaction. Why were the results different? Okay, this brings us to that second EQ for today, things that can affect reaction rate. So rate is thinking of like how fast something goes in a certain amount of time. So what makes something a slow reaction versus a fast reaction? So first of all, concentration. So I told you that in that demo that there was a saturated solution, meaning it had lots of particles per the amount of liquid or the amount of solution. And then there was a 0.1. Well, that 0.1 is a small concentration, meaning that there's not very many particles per amount of water. So there's not as many particles to react with. So if the concentration is low, you'll have a slow reaction because there's not as many particles to react. If you have a high concentration, it'll go much faster because there's just that many particles that can interact with each other and cause a reaction. The other one is particle size or surface area. So if you have really little pieces, there's a lot more places where the particles can interact. If you just have one big piece of a reaction, like think about a big chunk of something and you throw it in a reaction, it can only react with the outside of that big chunk. But if there's lots of little particles, every little particle can attract all the different little particles that it's being mixed with. So particle size, when they're smaller, more surface area, that'll be a faster reaction. Big chunks or not very much surface area, that'll be a slower reaction. Temperature, think of temperature as energy. If you have more energy, something can react faster. If it has lower energy, it will not react as fast. There's something called catalysts. We've mentioned that earlier. A catalyst is meant to speed up reaction. That's the definition. But there's also something called an inhibitor. So if I'm doing some type of chemical reaction and I don't want the reaction to go quickly, I can add an inhibitor, which will purposely slow down that reaction. Because maybe it's a reaction that needs time to finish, or I want it to last longer, like some sort of medicine in my body. I don't want it to react super fast because then that medicine is just gone and maybe then it won't do what it needs to. Or if the reaction is dangerous, so I'm trying not to produce as many products, that could be a reason I use an inhibitor. And then catalyst would be just all the opposite. I need the reaction to go fast. I want it to. I want to get the results quicker. So then that would be something that can affect it. The last one that I'm going to mention is really only if you're dealing with gases. Higher pressure means you're forcing the particles to interact a lot more, so you'll get a faster reaction if you're dealing with gas particles. Lower pressure means that those particles are not going to interact as much, so if those are gas particles, that'd be a slower reaction. So again, as a chemist, we're not just thinking about just like level one kind of definition stuff like, oh, what is synthesis? What is combustion? But we also want to start adding in these skills of predicting products and what affects a reaction. And as a chemist, like what do I want to do to create this reaction? It's not just randomly mixing stuff together. So that gives you a little bit more background about things that can affect reaction rate. All right, and now that brings us to our fifth type of reaction, which is double replacement. The definition is you take two compounds and they form two new compounds. If it's an ionic compounds, they would switch partners. So if I have Na and Br and Ba and Cl, Na, which is positive, goes with Cl, which is negative, Ba, which is positive, goes with Br, that is negative. So you've got that double replacement reaction. And then just a reminder or just a connection, all those precipitate reactions you did in Unit 2, those were examples of double replacement reactions. All right, finish off all of this learning with a level 3 question. So think about some big kind of brainy idea, a prediction, a judgment, an argument, something like that. But then we got to finish off with our last demo on double replacement. Let's check it out. Welcome to demo time. The demo I'm going to show you right now is the one for double replacement. So remember, the idea with double replacement is that you start with two compounds, and those two compounds are allowed to react. And what often happens is the ions of the two compounds switch partners. So you've got a positive and negative of one compound and a positive and negative of another compound. And so the positive of the first goes with the negative of the second. the negative of the first goes with the positive of the second. So what I have here is I've got, happens to be copper 2 nitrate. So copper is the positive, negative is nitrate, copper with a +2 charge. And then I've got sodium sulfide. So sodium is the positive and sulfur, so sulfide is the negative compound. So you can see that the sodium sulfide kind of looks like water. That's probably how we would describe it. It's an aqueous solution, so it is sodium sulfide mixed with water. And then I've got my copper 2 nitrate, the copper mixed with water, copper 2 nitrate, also aqueous solution mixed with water. So we see we've got these two solutions we can see through. This one happens to be blue, maybe kind of like mouthwash or Gatorade. And then we've got our clear, so it looks kind of like water. Mix them together. Ta-da! All right, so what we end up with is sort of this kind of greenish color, which is not exactly what you would expect, given that you're starting with blue and clear. And then you can also see that it's a little bit foggier. So if you think of like the clearness of what it started like, so you get kind of this precipitate that forms. So our precipitate reactions like we did in that lab, the new compound is insoluble. Chemical change shows us that this has something new. So old bonds are broken, new bonds are formed. Precipitate and color change, definitely a chemical reaction. Double replacement. All right, so then that brings us to the end of our second day of this new unit on equations. Here's your to-do list to finish up. So finish any COSTA questions if you didn't finish them during the notes, and then go back and write a summary for today's notes, which should answer the EQ. And then I do want to remind you about that balancing equations assignment from the last time we were together. Submit that worksheet. And then I do have an assignment for you to get started on it. I call it mega practice, not because it's super, super long, but because it shows and puts together so many ideas in chemistry. That's the mega practice part of it. Now, depending on what day you're watching this video, this assignment is meant to be due after our next class day. So the next day you have class, so whenever your day 3 is, because today is day 2, it will be due that next day. So day 3, you'll have time to ask questions, to compare answers, get some help, but then it will be due the next day. If you want some immediate feedback and check to make sure you're doing things right, the Unit 3 unit practice problems, so UPPs, are in the Week 5 folder on Schoology. You can do the next set of problems, check your answers, see if you know what you're doing, and ask for help if you don't. Just a reminder that Unit 2 lab report should already be done, so make sure that's submitted. If you have questions on it, make sure that you're checking in about that as well. All right. Thanks so much for listening. We'll see you at our next Zoom. Bye.